In this video, we're going to be looking at the concept of torques and applying them to an application known as static systems. What are we going to do? We're going to first review what a net torque is on an object and how to find it. We're going to define the term static system, and we're going to use the net torque of a static system to find an unknown force when there are several unknown forces in that system. Why are we doing this? Because in most real-world cases, torques play a vital role in analyzing the systems where there are several unknown external forces acting on that object or system. Now, it's important to note that Newton's second law of motion, the net force acting on an object or system equals the mass of that object or system times the acceleration, is always true. There is no exception. This is a law. It is always true no matter what. But sometimes it may not be enough to actually solve a question or analyze a system where forces are involved. Here we have two cases of two people holding up a beam. If I take a look at the first case where I have the bar with no weight on top of it, and I draw a free body diagram, which is always the first step in any problem dealing with forces, I can see that I have the force of person A and B on the edges of the rod lifting upwards, and the 20 Newton force of gravity pulling down on the rod at the rod's center of mass, which is directly in between persons A and B, equidistant from each. I can now say that the net force on that rod must equal the mass times acceleration, and if they're holding the rod level and still, that means there is no acceleration. This means that the force that person A exerts plus the force that person B exerts must equal the force of gravity. Now, instinctually, I want to say that the force of A must equal the force of B because they're working together to hold up this bar and they're working equally. And in this situation, that seems to make a lot of sense, and instinctually, it really does feel true. Now, if I want to take a look at that second case where I have a 10 Newton block on top of the 20 Newton beam, I still start with the same process where I'm going to go with a free body diagram. Here I can see that I have two forces going down instead of just one. So the total force in the downward direction is 30 newtons. The total upward force must still be Fa plus Fb. So using Newton's second law, net force equals ma, I can easily see that force of A plus the force of B must equal in the end the 30 Newton force which is going down. That's the combination of the negative 20 and negative 10 Newton forces that are acting on the rod. Now, if I employ the same logic I used last time, where each person must be working equally hard, I can split that 30 newtons into 15 newtons for each person and say that each person is working equally hard to hold up this beam. So this would be very much like the scenario that we had over here. However, to be very honest, that doesn't seem quite right. Typically, when people are holding up objects where the weight is not evenly distributed, we often have a side that we consider the heavy side, and we have a side that we often consider the light side. And you always put the weaker person holding the light side and the stronger person holding up the heavy side, because that side requires more force. That means this doesn't seem to be quite right. This one here seems logical because everything is balanced evenly. However, in case 2, that's not going to be the situation. Unfortunately, Newton's second law then doesn't allow us to solve this because we have two unknowns and one equation, and that is a totally unsolvable situation. We need to use another tool either to replace or work with Newton's second law. So as powerful and as useful as Newton's second law of motion is, the truth is we can't use forces all the time to solve every problem. Sometimes we have to come up with something else. So I've always been told, if you can't force your way out of a problem, should torque your way through it. One of the simplest situations that we're going to look at is known as a static system. Static systems are a classic situation that we deal with bridges, buildings, and roads. These are all structures that have no motion. That means they have no acceleration. And a static system is any situation where there is no acceleration of any type. That means there's no translational acceleration, there's no centripetal acceleration, and there's no rotational acceleration. Now, it's very important to be clear. Static systems can move. They just cannot accelerate. So if you have a constant tangential velocity, a constant angular velocity, those situations are still static, and everything we're doing here will hold true. The most common situation that we see is a system that is at rest completely. Unfortunately, that leads to a massive misunderstanding that to be a static system, you must be at rest, only because we see it so often. But again, you can in fact be moving. You just can't be accelerating. To be static, there are only two requirements. The first one is that the net force acting on the system be zero. This makes complete sense because the net force is what causes tangential and centripetal accelerations. So if there is no net force along any of the possible axes, then there is no acceleration. And the first part of the requirements of being a static system is met. There is no acceleration in a tangential or centripetal manner. The second requirement is that there is no net torque on the system. That makes a lot of sense as well, because net torques is what's going to lead to angular acceleration. Again, there is a very specific equation that we'll work with later on. We're just not using it right now. But torques create angular acceleration. So if there is no net unbalanced external torque, there is no angular acceleration. So by analyzing forces and torques on a system that is static, we can find everything that we need. Now let's take a look at that first case again, where we have two people holding up a 20 Newton beam. The very first step that I have to take in solving any problem involving forces is a free body diagram. I need a tool to visualize the forces acting on that object or system so I can write the correct force equation to solve for whatever it is I'm looking for. Likewise, if I'm going to be working with torques, I need to create a torque equation. It's very hard to write a torque equation correctly if I don't have a visual of those torques acting on the system or object. So just like a free body diagram, I also have to create a torque diagram. The easiest way to do this is to draw your bar underneath your free body diagram, like you see I have right here. The diagrams line up edge to edge. That is incredibly important for making your life easier when drawing out your torque diagram. Once you draw out your beam, you need to pick a pivot point. Sometimes you're told where the pivot is, sometimes you're not. If you're not told where a pivot is, pick an arbitrary point and you can work from there. I am personally picking the one that's on the far left side. I often find that to be the easiest reference for me. The next step is to draw out the torques. I don't have to solve for the torques. I simply just have to draw them out. To do this, I'm going to follow the force acting on the object and have it twist my diagram here, if you will, around that pivot. So for example, if I take a look at force A, that would be along this green line here and trying to pull this guy straight up through the pivot. Any force pulling through the pivot doesn't try to rotate anything. There's no radius. So since this is not trying to create any torque, I'm going to leave this one as a blank and simply erase this line. This 20 Newton force is pushing downward. So if I follow my dashed line that I have here to this rod, I can see that this would actually push the rod down and around my pivot. So I need to go around the pivot. So I can see that this torque will go in a clockwise direction. How much torque is there? I'm not worried about that right now. I'm just simply drawing out the torques and the directions in which they would try to rotate the rod. This force over here, FB, is trying to lift the rod upward. So if I follow my alignment line here, I could see that B would be trying to pull the rod up, and that would twist the rod around the pivot in a counterclockwise direction. Please notice all torques must go around the pivot. I'm not drawing up or down. I'm drawing clockwise or counterclockwise. That's based on the direction of the forces from my free body diagram. I really cannot draw out my torque diagram without my free body diagram there to assist me. So step one, as always, is to draw a free body diagram for any situation where forces are involved. Now that I have the torques drawn out, I can see if I can solve for some of their values. This torque right over here is created by this 20 Newton force that's acting a distance of 1 meter away. So this torque must be 20 newtons times 1 meter. And since this is in a clockwise direction, I can say that's actually a negative torque, indicating that it's a clockwise direction. This torque here, acting on the edge of the rod, is created by this force of person B that I do not know, and they are a distance of a full 2 meters from that pivot. So I can say that this torque has a magnitude that's equal to FB, a force I do not know, times the distance of 2 meters. Since this torque is in a counterclockwise direction, I'm going to label it as a positive to indicate that it's a clockwise direction. I now have my two diagrams that will allow me to create the equations I need to solve this problem. If I look at just the free body diagram, I can write out the force equations that I had before. The net force equals ma, and Fa plus Fb must equal 20 newtons, since there is no acceleration and no net force. Again, I don't know which force is larger or smaller, if they're equal. I feel they might be equal, but I could be wrong. If I look at torques, however, I can now say that the net torque of the system is 0, which means the negative 20 newtons times 1 meter plus the Fb times 2 meters must equal 0. Please notice I have only one unknown in this equation. One unknown, one equation is a very solvable situation. Two unknowns in one equation is completely unsolvable. So now I can turn around and solve for FB, and I can see that FB is equal to 10 newtons, which was half the weight, which is what I felt the answer should have been, just in the fact that everything seems to be evenly distributed. Now if I want to solve for force A, I can easily turn around and use Newton's second law again from the equation I had earlier on, and simply substitute in the force B that I now know. And I can see that Fa is also 10 newtons, which makes a lot of sense, because if FB is carrying half the weight, Fa has to carry the other half of the weight. That spot has got to be picked, otherwise you get the wrong answer. That's a legitimate concern that some people have, so let's test that out. The first thing I'm going to do, regardless, is I have my free body diagram, just like I did before, because again, that creates the visual for everything that I'm going to be working with, be it my force equations that I have off to the side so I can use them if I need them, as well as the torque diagram that I'm now about to develop. Again, I have my torque diagram lined up with my free body diagram, so I can just simply draw my forces and torques as they are all lined up. Starting at this edge over here, I can see that FA would be pulling straight up. So FA would pull up and around my pivot. That makes my torque go in a clockwise direction. My force of gravity is pulling straight down. This would try to do this through the pivot, which is not trying to twist. So there again is no torque through any force that's going through the pivot. So I'm going to ignore the force of gravity in this case because it's not trying to twist the rod. B, like A, is lifting upwards. But since it's on the right side of the pivot, up and around means in a counterclockwise direction. So the torque on the left side would be FA times 1 meter, and that would be a negative sign since it is clockwise. And the torque on the right side of the pivot would be FB times 1 meter, positive because it's counterclockwise. I can now write out my torque equation, and I can see that the net torque must equal 0 since there is no rotation or acceleration of any type. And I can now see that FB must equal FA. My torque equation in this case is not giving me any values. It's only telling me that the two forces must be equal. However, if I now combine my torque equation that I have here with the equation I got from my forces up here, I can combine them to solve for one of my unknowns. And by simply substituting FA for FB, I can turn around and say that 2FA equals 20, so FA is equal to 10, which means FB is also equal to 10. This is the same answer I got last time. So picking a different pivot point really doesn't impact what my answer is going to be. The requirement to be in a static case is that the net torque around any point of the system must be 0. So I can pick any point I want as my pivot. I always personally try to pick pivot points that are more strategic than others. For example, in this case, I did not get to work with the force of gravity, and I was stuck with two unknowns in my torque equation. That's not very convenient. Typically, I prefer to pick a pivot point where I lose one of my unknowns. One of my unknown forces going through the pivot, and another unknown is not. But that's a personal preference and a style choice. You can pick any pivot you want. It will always work if you follow the process. If I was to have picked the right side of the beam where FB was, I can still solve for my forces as well. In this case, again, here's my free body diagram, just like it's been before. Here are my force equations, and I'll be able to use them later on if I need. In this case, FB is lined up with the pivot. So this would try and pull the pivot rather than twist around it. So FB will create no torque. Thus, we will not consider it on our force diagram. Consider it on our torque diagram. The 20 Newton force would be pulling the rod down, which would be down and around the pivot. So in this particular case, since the pivot is on the right side of the force of gravity, this is going to cause gravity to twist the rod in a counterclockwise direction. FA, pulling upward, would take this end then and lift the rod up and around the pivot in a clockwise direction. This means the torque created by FA would be negative FA times 2 meters, while the torque created by gravity would be 20 newtons times 1 meter, and in this case it would be a positive because that's the one that is going counterclockwise. I can now use my torque diagram to create my torque equation, and I can now say that the net torque equals 0, so that positive 20 times 1 plus negative FA times 2 must equal 0, and so FA must equal 10 newtons. Knowing that FA is 10 newtons, and knowing that FA plus FB must equal 20 newtons, I can now go ahead and solve for FB, which again was the 10 newtons that we knew from before. If you really wanted to, you could actually avoid the force equations completely and just do torques twice. You could do a pivot on the right side of the beam and a pivot on the left side of the beam. But please notice, even if I'm skipping the force equation, I'm not skipping the free body diagram. The free body diagram is the most important tool that we have in understanding any force problem. And a torque problem is a force problem because torques come from forces. Now let's take a look at a situation where the weights were not evenly distributed in the middle. Again, if I draw my free body diagram of the system, I can see that FA plus FB must equal the 30 newtons going down. But from what we've seen in the past, the forces of A and B are probably not going to be equal because they'll have different amounts of leverage. Torques play an important role here. So the forces alone fail in this situation. Logic was able to kind of help me out when I had everything distributed evenly, because we can go everything must be divvied up evenly. But in this case, FB must be stronger than FA because there's more weight near FB. FB has less leverage in this system. The only way I'm going to be able to solve this effectively, or really at all, is by using a torque diagram and a torque equation. So if you notice, I have my free body diagram right up here, and I have a setup for my torque equation right below it. Since I can pick any pivot I want, and I do not know FA, I'm picking where FA is to be the pivot point. This way, that will disappear, and I'll only have FB left. So my torque equation will allow me to solve for one of the forces right away. So, in this case, like I said, FA is going to create no torque going through this pivot. Working out from the pivot, I can see I've got my 20 Newton force of gravity pulling the bar down. So, starting from where that's pulling on the bar, I have 20 newtons going down and around the pivot, and that's at a distance of 2 meters. And since this is in a clockwise direction, that would be a negative torque. Likewise, I have this 10 Newton force that's also pulling down, so that'd be down and around in the same clockwise direction. So that would also be a negative times 10 newtons. But I need to know what my distance is from my pivot. Now they did not give me that. I was told that the distance from this end is 0.3 meters. So I'd have to subtract out 0.3 meters from the full 2 meter length of the bar to find out that my distance from the pivot is 1.7 meters. So with that, I'll put in the 1.7, and I can now go ahead and calculate out that torque. FB, acting on the far end of the bar, is going to go up and around the pivot, and that would result in a counterclockwise torque. So I'll call this one FB times its full length of the bar from the pivot, which is 2 meters. With all the torques drawn out, I can now write out my torque equation. And by saying the net torque equals to 0, I can now easily solve for FB, which comes out to be 18.5 newtons, which is definitely more than half of the 30 Newton force. It's definitely more than 15 newtons. Now, if I want to find the force of FA, I can go back to my force equation and say FA plus FB equals 30 newtons. And since FB is 18.5 newtons, FA must be 11.5 newtons. If I was to look at the situation with the pivot being on the right side of the bar where FB is, I'll come up with a different torque equation that should still work for solving for one of the forces. Since the pivot is now on the left side where FB is, FB will create no torque on the pivot, and I'll be able to solve for FA directly. Starting out from the pivot, I see that I have this force of gravity from the 10 Newton block that's going to go down and around the pivot. That would be 10 newtons of force times the distance of 0.3 meters that they gave me. And since this down and around is going to go in a counterclockwise direction, this must be a positive torque. The 20 Newton force also will go down and around, like the 10 Newton force. So that will result in a counterclockwise torque. And that will be 20 newtons times the distance from the pivot, which is still, again, 1 meter. And that would be a positive torque. FA, lifting upward, would go in a around position of clockwise. So that would make this a negative torque in this case. So FA times its distance of 2 meters from the pivot. With my diagram, I can now set up my torque equation. Net torque equals 0. Each one of my torques adds up to 0. And then I can solve for FA, where I see it's the 11.5 that I found before. Now, if I had solved the torque situation last time to find FB, and I use the torque situation again to solve for FA, I'm done. Otherwise, I would have to use Newton's second law equation and solve for FB. And please notice, even though I picked a totally different pivot, I found the exact same forces for FA and FB as I did when I picked on the left-hand side. Again, you never have to stress on where to pick your pivot when solving these static systems. Any point works. You just have to pick the point that works best for you. This situation looks more intimidating than the situations we've looked at before. However, it is no more involved or complicated than anything else that we've done. This situation is often called a boom scenario, referring to what you might see on a sailboat. The boom itself is this 10 Newton bar that is 4 meters long, jetting out of a wall. We have a string that is holding the boom level at an angle of 30 degrees. This string is attached to the wall as well. On top of this, we have a 2 Newton weight 1 meter from the edge of the boom farthest away from the wall. On top of the uniqueness of the scenario, we're not being asked to find one thing. We're actually being asked to solve for several things, such as the tension force in the wire that's holding the edge of the beam level, as well as the force vector that the wall itself is exerting on the edge, because the wall must prevent this side from sliding, as well as prevent this edge from going through the wall. This results in some net force vector that the wall is exerting on the bar that would be in this type of direction. So we're looking for the force of the wall as well as the tension force. And these two forces do not need to be equal in any way. So of course, the very first thing that I'm doing is I'm drawing a free body diagram. The tension force I know is at an angle of 30 degrees. So I'm going to break this up into components, as we can see right here on my free body diagram. I've got the force of gravity from the 2 Newton object, the force of gravity of the 10 Newton boom, which is directly at the center of the boom, since that's the center of mass. And since the force of the wall is going to be at some angle, I can break that into components. And since I have no information at all about this force, I'm going to call the one along the x-axis Fx and the one going along the y-axis Fy. And that's all I can call them for right now. With the tension, I can at least use sine and cosine of 30 degrees because I was given the angle. My free body diagram is a little bit more involved since it is working with 2 axes. So when I'm working with my force equation, I'm not working with just one equation, but 2, one for the x, one for the y. So what I'm going to do is I'm going to t-chart my force equation. So I have one for the x-axis, one for the y-axis, just like we did with projectile motion in any other 2-dimensional system. For the x-axis side, I can see that I have Fx minus t cosine 30 equaling 0 newtons, since Fx is going to the right and t cosine is going to the left. And I know that Fx equals t cosine 30, which would be awesome if I knew what Fx was or t. But since I don't know either one of these, I really have no answer yet. Looking at the y side, I can turn around and say Fy plus t sine 30 plus the negative 10 plus negative 2 must equal 0. In short, the 2 forces up must equal the 2 forces down. So Fy plus t sine 30 must equal 12 newtons. But again, I don't know t, so I can't solve for Fy. And I can't solve for Fy because I don't know t. And I can't cross over like we did in projectile motion because I don't know Fx to use for t. So the reality is, looking at just forces, I can't solve for anything because I have way too many unknowns. While I do have 2 equations here, I do have 3 unknowns. My unknowns are in fact Fx, t, and Fy. So I need a 3rd equation if I'm going to solve this problem. And I'm going to get that 3rd equation by way of my torques. So I have my torque diagram set up right underneath my free body diagram. I'm going to pick a pivot point that is going to make my life a lot easier. I'm going to pick where the wall is for the very simple reason I do not know what these forces are at all. And since they will both go through the pivot, they will not create any torque. They'll be eliminated from my torque equation, allowing me to solve for t, because that will be only one unknown. That's the trick to this. Pick a pivot point that eliminates as many unknowns as possible with the exception of the one that you're trying to find. Also, since I'm picking where the wall is, t cosine 30 would push right through it. So t cosine 30 would go this way, Fx goes this way, Fy goes this way. All 3 of these forces go through the pivot, which means none of them actually create a torque. So I do not need to consider these at all when drawing out my torque diagram. Please notice 6 forces have been reduced down to only 3 forces when dealing with torques. This is a lot simpler than it initially looked to be. So now if I start from the wall and start moving out, the first force I come across is the force of gravity of the rod itself, which is 10 newtons. That's pulling the rod down and around the pivot point in a clockwise direction. So that is a negative torque whose force part of the equation would be 10 newtons and whose distance is 2 meters, 1/2 the length of the rod. Moving further out, the next force I come across is the force of gravity of the weight. So that will also go down and around in a clockwise direction. So that also is a negative torque. The force part of that equation would be 2 newtons, and the distance there would actually be 3 meters, since that's the distance from the wall or my pivot. The rod is 4 meters long. The distance I'm given is 1 meter from the right side, which means it's 3 meters from the left. The last force I come across that's going to produce a torque is the T sine component of the tension. So I'm going to draw that up and around the pivot in a counterclockwise direction. So this will be a positive torque. The force I'm going to put in is T sine 30, because that is the component that's going to create torque, times the distance of 4 meters. Now that I have all my torques drawn out, I can write out my torque equation. I can start by saying that the net torque is equal to 0, and so negative 10 times 2 plus negative 2 times 3 plus T sine 30 all times 4 is equal to 0. I only have one unknown, the T. So I can now solve for that using algebra, and I find out that the tension is 13 Newton meters. So now I can take the 13 newtons that I know the tension is and substitute it into the T in my Fx equation. Remember, Fx is the x component force of the wall pushing on the boom. So that x component of the wall is equal to 13 cosine 30, which is 11.26 newtons. Likewise, I can take the 13, substitute it into the T for the y equation I have, and find that the y component force of the wall is 5.5 newtons. Since these are two components of the one vector of the force of the wall, I can then draw a right triangle and solve for the hypotenuse and angle for the vector force that the wall is exerting on the boom. So in the end, we can say that the wall exerts a force of 12.53 newtons on the boom at an angle of 26.03 degrees. Just like we can say that the tension force in the wire is 13 newtons at an angle of 30 degrees above the boom.